Hello and welcome to this video where I want to talk about the value and reference subject. And this subject is of the utmost importance within RealFlow graphs. For C and C++ programmers, this is a very familiar and well-known concept. But even though you know very well what value and reference means in terms of programming, I encourage you to continue watching this video. And I think the best way to explain this is through an example. Okay, so let me do that. First, let me just change the layout a little bit so you can see better what I'm doing. I'm going to change the panel here to a batch graph. I'm going to give more space to the batch graph and leave the single view right here in a smaller place. I'm going to create a cube. Okay. So what I'm going to do first is to bring to the graph that cube. So for that I have a node which is getObject, uppercase node, getObject. It is here, and I'm going to type here the name of the node that I want to bring, cube 01. Okay. Now from that cube, I want to get the mesh. For that we have the getObject mesh. As I explained it in a video before this, the video about the data types, most of the times you want to use a mesh instead of a object mesh in your RealFlow graphs. Especially in this example, I'm going to use the mesh textselect node, and if you right click on this pin, you will see that the type that is allowed here is mesh, not object mesh, so I cannot connect those nodes together. So for that, we have to transform this object mesh to a mesh. So for that, we have one node object mesh to mesh. Okay. Okay, now I'm going to create an array of 5 elements that are going to be 5 cubes. In this particular case, I'm going to be working with the mesh of those cubes. So for that I have one array mesh constant that in this case is going to have 5 elements. So here I am creating an array of 5 elements, and every single element, it is the mesh of the cube. Okay, so I'm going to get one element of that array, for instance, say the element with the index number 2. For that I have get array mesh element. I will connect the array input, and for the index I will be using the number 2. Okay. So now I'm going to get this mesh and textselect, and finally I will display that mesh. I'm going to be displaying in wireframe, and I'm going to choose the red color here. Okay. I'm going to get also another different element of the array, say for instance the number 3. And in this case I'm not going to tessellate the mesh of the element 3. I'm going just to display this case, this is gonna be using a green color and is a wireframe as well. And finally, I'm going to create an evaluator node, and I'm going to be adding two different, one input more, so I can connect the two display nodes to the evaluator. Okay, so just let me go back to the construction of this graph. I am getting the object from the RealFlow scene. I am getting the object mesh. I am transforming the object mesh to can say standard mesh that can be used inside the graphs. And I am creating an array of 5 elements where each element is a mesh, the mesh of the cube. With this node, we are accessing the second element. Actually, it's the third element because the array's indices starts on the 0, 1. And I am going, with this node, I'm going to get the fourth element. I'm going to tessellate the element at the index 2, but I am not going to tessellate the other one. And I will be displaying both. So if I execute the graph, you see here that since that I am displaying both together, you cannot see the green color. But if I disconnect the first one and I run the simulation graph again, you will see how, excuse me, I'm going to remove that so you can see only the green one. Here we are. So you can see how, even though the element at the index 3 has not been tessellated, it is shown here that it's already been tessellated. So what's going on here? So what's actually going on here is that we don't have 5 copies of the mesh of the cube in memory. We have only one mesh, and all the elements in the array are just references to that mesh. Let me show you a picture of this situation. Here you can see this is the array of with 5 elements, but the elements are just references to the original mesh. So even though you tessellate one single element of the array, the other elements are referencing the same mesh. So all of them are going to be showing the mesh tessellated. All the arrays of complex types and SC node types, are always by reference. And the reason why is, again, efficiency. Imagine having a huge particle system and creating an array out of it. You will end up having a massive memory consumption. And this is, you don't want that most of the times. You can change this default behavior. In this last example, I can easily create a copy of the mesh and perform the tessellation on that copy. Let me do that. Go back to RealFlow, and here, instead of tessellating the element of the array, which is we know now that is a reference, I'm going to create a copy. Okay, let me display this mesh here. I will change this to the red color. So now, if I run the simulation, the graph again, you see here that we are displaying the tessellated mesh, but if we don't display the texelated cube, you see how now the element at the index 3 is not texelated. Here we are working on a value instead of on a reference, and that's the difference between the two concepts. Let me show you a picture of that. Going back to my slide, and in the next slide you see here how the original cube is here and all the elements in the array are just reference. When I am doing a copy, I am just duplicating this mess in memory, and now when I perform the texelation, I am performing the texelation on that copy and not on the original one. So all the reference are just pointing to the original mess. I will continue talking about value and reference in RealFlow graphs. To explain this, I think I'm going to follow an example that is going to be easy for you to understand what's going on. So I'm going to be adding two different arrays of real values. It doesn't matter what value we are going to be using here. Let's say, for instance, 2.0. I'm going to change the name. 2.0. Okay. And I'm going to be needing an array num constant. Okay, so this node will create an array of 5 elements where every single element in the array is going to be having a 2.0 value. I'm going to copy and paste, and going to change the value here. Let's say 5 or 50.0. The size is 5 as before. Okay, let me change the name of this node to be 50. Okay, so I'm gonna bring an add node that will add both arrays together. So this node will be adding every single element of this array with the other one. So the first element in this array with first element in this one, the second with the second in the other one, etc. And then I'm going to print the result. So this is the message print. But because this is an array, I need to convert the real numbers to a string. So I have one node which is real to a string, I believe. Yes. Okay, so I'm going to plug this pin here, this here, and to finish my graph, I'm going to be adding an evaluator node. So if I did it the right way, when I execute this graph, you see here the result. So it's 50 plus 2 is going to be 52 for every single node. So now let me add copy and paste another array here with the same size, 5 elements, but let me change the number. Let's say it's a big number so we can see better the difference. And I'm going to change the name as well. Okay, now I'm going to add this array with this one. And I'm going to duplicate those nodes because I want to print out the result of the operation. And because I want to explain the importance of the order of the evaluation, I'm going to add a new input to this evaluator, and I'm going to plug this output pin to this one. So now let me clear the message panel. So this is in layout, clear messages of Control-Shift backspace. If I run my graph again, and you see here the result of this branch up here, which is 50 plus 2, 52, and then the other branch here, which is adding 50 and 1970, which is actually this number. Okay, so far so good. So now you see those small triangles here? If I left click on them, I am going to be able to create an internal connection. So what this internal connection means? Basically it means that the array that we have here is going to be having the result of this node here. If I remove this, what this node is doing is creating an internal array where it contains the result of the addition. So in this case, we are going to have one array, another one, and a third one created internally here. So sometimes you don't need the input values anymore. So instead of creating an array inside this node, you can create an internal connection, meaning that this array is going to be using here for the result. So you are saving one array here. In this case, we have only 5 elements, but imagine that we are working with a particle system having 50 million particles. You can save a lot of memory if you follow this strategy. But I want to draw your attention on the issue that because we are modifying this array, the result here, when we evaluate the second branch right here, is going to be different. So let me run the graph again, now that I've created this internal connection. So Control-Shift backspace to clear the messages, and I'm going to run the graph. So the first branch has been evaluated and the result is 52 as expected. But then when we evaluate the second, the bottom branch, you see here how now we are having this value, which is actually adding this number to the result that was stored here. So this number plus 52, which is actually this list of number here. Please notice how the evaluation order is very important right now. In an evaluator node, if it has a list of inputs, they are going to be evaluated in the order from the top to the bottom. If I have two different evaluators in my scene and I'm connecting this way, you don't know what is going to be the order of the evaluation, so you cannot, we cannot guarantee what is going to be the order. So if you want to make sure that the order of the evaluation of the graph is following one specific order, make sure you are using just one evaluator and adding more inputs for that evaluators. There are nodes that have internal connections by default, and you cannot change them. For instance, let me bring the particle at the node. You see here that it has an internal connection already. These are nodes that especially work with complex types and then modify the data and provide the same data modified at the output. And in this particular case, you can change the particle system by adding particles, but you don't want to create a new particle system inside the node. So you are going to be reusing the same particle system that you have in the input. Okay, so that's it for this video, and thank you for watching.